So in the previous lecture, we learned, the following lower bound, right? We proved that without PKI or any setup assumptions, Byzantine broadcast is impossible if at least n/3 players are corrupt. Okay, so we proved this lower bound together. And remember, I said during the lecture that this lower bound is in fact tight, in the sense that indeed, if strictly fewer than n/3 players are corrupt, we can indeed construct a Byzantine broadcast protocol. And this is we will learn today. So today, we are going to show that this is tight. And when I say tight, I mean in terms of resilience, right? In other words, what we will prove today is the following theorem. If strictly fewer than n/3 players are corrupt, then there is a Byzantine broadcast protocol that doesn't make use of PKI or any setup assumptions, that does not make use of a PKI or setup assumptions. Okay, so to prove this, we're just going to construct the protocol and prove it secure together. Again, remember we learned this voting-based protocol earlier. I mean, it was meant to be a straw man. That particular voting-based protocol was not secure against even one corrupt player, right? And today we are going to look at another like voting-based protocol, but this one actually, you can prove something interesting about it. You can prove if strictly fewer than 1/3 are corrupt, the protocol does give you a Byzantine agreement. Okay, so how does this work? And let's first recall the setting again. We have n players, and the n players are denoted 1 to n. And we are going to assume the designated sender is player 1, right? Just the problem formulation is the same as before. Designated sender is player 1. And we are actually going to make use of a hash function, public hash function h. So h takes in, let's say it takes in any string, and it hashes it to 1 to n. So it basically, we are going to use this as a random oracle that essentially elects a leader in every iteration. Okay, so we will model, I want you to think of this as a random oracle. And what a random oracle does is that, imagine every time you call h, right? So h is essentially the following function. Upon receiving x, if x has not been queried before, it selects a random number from 1 to n, and then it returns this random number. Okay, so else if x has been queried before, just return the same answer as before. Okay. So let's assume this is a random oracle, and then the protocol essentially goes in iterations. And let me talk it over first, and then I will write it down. So imagine, like, so the first thing is that everyone has a sticky bit. And the sticky bit initially, it's bottom. So it initially set to bottom, right? So bottom means I don't have any belief. So the sticky bit can have 3 possible values, like it's either 0, 1, or bottom, right? So we are trying to agree on a bit. If the sticky bit is not bottom, it means I do have a belief. And like during the protocol, as you will see, I will always try to stick to my belief whenever possible. So like I would always prefer to stick to my current belief, unless somehow convinced otherwise.
I have a question.
Yes, go ahead.
It's about the part before. So like, are we assuming that H is a random oracle, or is it a hash function that models a random oracle?
So random oracle actually cannot be realized with any deterministic function. It is kind of like a relaxation that we often make when we prove things. So we are like, so typically in crypto, right, we can take a public hash function like SHA-256, and oftentimes, like I think, initially cryptographers didn't know how to prove certain things secure, and they had to like make assumptions like if the hash function is like indeed completely random, like it's unpredictable, it doesn't have any algebraic structure that we can exploit, then let's say, the signature scheme would be secure. So although, we know that random oracles like cannot exist in the sense that no deterministic function can actually be a random oracle.
Okay, so it's just an assumption that we're making for the sake of the proof.
Yeah, so right now it's an assumption that we are making. There are ways to replace this assumption, like with like you can also think of a random oracle as a really exponentially long common reference string, and that's chosen a priori. Like there's potential ways to like compress it to a shorter one. Like you can choose a shorter common reference string a priori, and then like use a pseudorandom function in place of this random oracle. But like we won't go there in this lecture. We're just going to take the common approach and assume this is a random oracle. Okay, so essentially this means that we are assuming this hash function is kind of like unpredictable a priori. Okay. Okay, great. Thanks for this question. Okay, so now, so that's the role of the sticky bit. And then in every iteration, there's going to be a leader. So the protocol is more like the leader makes a proposal and then people will vote. And then they modify their sticky bit. Okay. And then the way to, calculate the leader is exactly to rely on this random oracle. I mean, except for iteration 1. The first iteration, the designated sender is going to be the leader, right? So leader, the definition, I'll write L sub R, and this denotes the leader of iteration R. And the definition of the leader is essentially L1 is defined to be 1, right? So basically the first iteration, essentially the designated sender is the leader. Okay, and then afterwards, for R greater than 1, we define LR to be essentially, you take this random oracle and you hash the current iteration and you get your leader. So the leader in some sense is elected at random in every iteration. So now the protocol, as I said, it's going to proceed in multiple iterations. So actually, let me clarify a little bit. So initially, everyone's sticky bit is set to bottom, but except the designated sender. The designated sender's sticky bit is actually set to its input bit, right? Because naturally, it believes in its own input. So let me write here, except in the designated sender, whose sticky bit is initialized to its input. Okay. So now here's the protocol. Okay, I'll just write the sticky bit again, just to be clear, right? So initially, the designated sender, the sender's sticky bit is its input. Everyone else's sticky bit is 0. Oh, sorry, it's bottom. Everyone else's sticky bit is bottom. Okay. So now we go in iterations for every iteration. Um, 1 to k. So k is the total number of iterations. It's a parameter. And so now we'll just leave it as a parameter. And later on, we'll see how to specify this parameter. Okay. So every iteration has essentially 3 rounds, right? Round 0 is like the proposed round. So in the proposed round, the leader will send a proposed bit to everyone. You make a proposal, right? You propose a bit B to everyone, where B is chosen as follows. So how do you choose the proposed bit? So as I said, use the rule of thumb, right? If I do have a non-bottom sticky bit, I prefer to propose my sticky bit. If my sticky bit is bottom, which means I don't have any belief, then I pick a random bit to propose. Okay, so very simple. If the leader's sticky bit is not bottom, just choose the sticky bit to propose. Otherwise, choose B at random from 0 and 1. So I propose a random bit if I don't have any belief. Okay, so remember now we don't have signatures. Or when I send message, I'm just going to directly send the message to all the other players. And the channels are authenticated. And this was actually a question that was asked in the previous lecture, right? The channels are indeed authenticated. So when I receive a message, I know who actually sent the message, but the message doesn't have a signature. Okay. So that's the first round of the round 0 of the iteration, right? So now in the second round of the iteration, essentially everyone's going to vote. So I will choose a bit to vote and I will send everyone the vote. And then the vote, how do I choose a bit to vote? The same idea. If my sticky bit is not bottom, which means I have a belief, I'm going to vote on my sticky bit. I'm just going to ignore the leader's proposal. Whatever he or she proposes, I don't care. I'm going to vote on the sticky bit. If I don't have a sticky bit that's not bottom, which means I don't have any belief, then I'm going to listen to the leader. Whatever the leader has proposed, I will vote for that bit. I mean, sometimes the leader can be malicious, right? The leader, for instance, let's say, didn't propose anything, or the leader proposed both bits. In that case, I'm allowed to pick arbitrarily. Okay, so let me write it down. So actually, let me write down the vote first, right? So in round 1, everyone votes on a bit. Essentially, to vote on the bit, you just send the bit to everyone. And the bit voted on is chosen as follows. So if the player has a non-bottom sticky bit, just choose the sticky bit, because that's my belief and that's what I prefer. Otherwise, choose the bit proposed by the leader. But with the following exception, right? I mean, it's possible that LR is malicious. So just in case, LR proposed no bit or both bits. In this case, I just pick arbitrarily. I don't care. Okay, so that's the voting round. And now, finally, in round 2 of this iteration, what will I do, right? The most natural thing, I will collect the votes of this iteration, and then, I may decide to modify my sticky bits based on the votes I collect. Okay, so how do I modify my sticky bits? If at least 2/3 players voted on the same bit, I'm going to modify my sticky bit to that bit. Otherwise, I will set if let's say there's no supermajority, like I don't see 2/3 votes on either bit, then I'm going to set my sticky bit to bottom, right? In one case, there's a strong signal that supermajority of players believes in the same bit. In that case, I will modify my sticky bit to that bit, right? Because that reflects my new belief. In the other case, there is no strong signal, like, either everyone's voting for different bit or people are kind of diverged in their votes. In this case, I will set it to bottom. Yes.
Yeah, so like when you vote, are you allowed to vote 2 bits if you are malicious?
Yes, you are allowed to vote for both bits if you are malicious. So
then
if
it's possible
honest,
that we have both bits to be over 2/3, right?
So yeah, that's actually an excellent question. It turns out no.
Because you only have 1/3 of corrupted people.
So yeah, so let me write down the protocol, and the next immediate thing I will do is to prove that lemma. So you're actually a little bit ahead of me. Okay, so it's a really excellent question. So let me just finish writing it down. Everyone tallies the votes it has received. If at least 2/3 players. So when I say 2/3, right, it could be it's not divisible by 3. And what it actually means, it's like take the ceiling. So I'm not going to write the ceiling because this is also precise. Like if it's a fractional number, I just mean 2/3. Okay. If 2/3 players voted on the same bit B prime, update my sticky bit to B prime. Else, if neither bit gained 2/3 votes, update its sticky bit to bottom. So, okay, so finally, after k iterations, I'm just going to output my sticky bit. So that's the entire protocol. It's quite natural. It's like, you know, kind of inspired by this naive voting protocol, but, you know, with some tweaks. Like, and most significantly, the trick is like, I'm going to kind of maintain a sticky bit, and I always prefer to, you know, stick with my sticky bit. Okay. So the first question that was asked by Junxi was that, like, you know, could it be possible when I wrote here, if one of the bits gained supermajority votes, I will modify my sticky bit to that bit. But is it possible that both of them gained supermajority votes? So the first thing we will prove is actually, no, it's not possible that both bits gained supermajority votes. And let me write it down. So in fact, I will, okay, so we have lemma. Let's call that lemma 1. So the lemma says at the end of the iteration, at the end of every iteration, it cannot be that some honest player has a sticky bit B that's not bottom, and another honest player has the sticky bit 1 minus B. So we cannot have opposite beliefs. So however, it is possible for some honest nodes to have, let's say, the sticky bit 1 and others have bottom. So that's possible. Like it's okay if, you know, some people believe it's 1, but other people don't have belief. But it cannot be the case that people have opposite beliefs. Like, you know, if I believe in 0, you believe in 1, that we don't want. Okay, so just let me note that it is possible, actually, that some honest player has sticky bit B, which is not bottom, right? It's in 0 and 1. And another honest player has bottom. Okay, so this is just a note. And now let's prove this lemma together, right? Why can we guarantee this? I mean, kind of the same intuition that Junxi already conveyed, right? So why? Because, you know, there are fewer than n/3 corrupt players. Okay, so the thing to keep in mind is that in this protocol, right, essentially all the honest nodes will vote uniquely in every iteration. Like if I'm honest, I will only vote on a single bit to everyone. If I'm dishonest, of course, I can vote on both bits. I can vote differently to different people. But at a high level, like, you know, if both bits actually got more than 2/3 votes, right? That's not possible because, like, you know, in some sense, honest people vote uniquely. So there can't be so many votes. Like only corrupt players can vote on both bits. So if you think about how many total like votes there are, like in some sense, there cannot be so many votes. Like for both bits to gain 2/3 votes, like in some sense, you know, we need to have 4/3 times n votes. Okay. So let's prove this together and we'll see why this is not possible, right? So we can, let's suppose some honest player, I, updates its sticky bit to some non-zero bit, sorry, non-bottom bit, right? In some iteration R. Okay, so for this to happen, okay, so let's actually assume some player updates it to B and another one updates it to 1 minus B, right? So we can do proof by contradiction. And another player also in iteration R. Okay, so we want to reach a contradiction. So for player I to update its sticky bit to B, right, which is not bottom, it must be that at least 2/3 of the people and I will denote this as denoted as SI, right? So this is the set of 2/3 people that voted on B. To player I. Right, so the only way for player I to set its sticky bit to B is if it has heard 2/3 players vote for the bit B. And I'm just going to denote that set who voted on B to player I as SI. And similarly, so I and J are both honest, right? Another honest player Similarly, we can conclude that J has heard 2/3 players vote for 1 minus B. And let this set of players be denoted as J. Okay, so now I want you to think about SI and SJ, right? So here are the players that voted for B to player I, and this is the set that voted for 1 minus B. So this is the set that voted for B to, let me just write it down, voted on B to I, and this is the set that voted on 1 minus B to J. And both sets has at least 2/3 players, right? So now I'm going to ask you, what's the size of this intersection? Like, how many players voted for B to I and voted for 1 minus B to J?
At least one, n over 3.
Yeah, so this intersection is at least n over 3, right? Is this clear to everyone? So remember, in total, there are at most n players, right? So if each set size, Si and Sj, both have size at least 2/3 n, then the intersection must be at least 1/3, right? Okay, so now I want you to think about this intersection, right? So observe that the adversary controls strictly fewer than 1/3. So what can we say about this intersection?
There must be some honest.
It contradicts with our assumption.
Yes, so who was, it was that Junxi, right? So Junxi said that there must exist some honest player in the intersection, right? Because, so okay, so recall the adversary controls strictly fewer than 1/3. Okay, so this means that there exists an honest player in the intersection Si intersect Sj. And now what can we conclude? Like, remember what I said about the honest players, right? What do the honest players do? Like, they will only vote on 1 bit. They're not going to vote on different bits to different people in every iteration. So we've essentially reached a contradiction, right? Because in this case, we concluded that this honest player voted for B to I and voted for 1 minus B to J. And that is impossible by our protocol definition, because in our protocol, the honest players will vote consistently in every iteration, right? So therefore we have a contradiction. Because honest players vote uniquely in every iteration. Okay, so this is a very simple lemma. Actually, sometimes this is also called the quorum intersection argument. And the proof, like, all it does is just pigeonhole principle, essentially. Okay, and then let's just scroll back and recall what the lemma says, right? We'll keep this in mind for the later part of the proof, right? The lemma says at the end of every iteration, people cannot have completely opposite beliefs. Honest people, it could be like some honest people believe in one, others believe in bottom, they don't have a belief. That's okay, but it cannot be, you believe in one, I believe in zero. That's impossible. Okay. Any questions at this point?
Yeah, I have a question. Can the set Si union Sj be greater than n?
There are only n players, so it cannot be greater than n.
But can a player pretend to have voted differently for both the sets?
A correct player can vote differently.
So in that case, if you have n by 3 minus 1 correct players, can't they pretend to create?
I mean, those players are in, like, if someone voted on B to I and voted on 1 minus B to J, then it would be in the intersection, right? I mean, the set contains only n players, like the.
I think the confusion stems from like the total votes, each node sees, like if the malicious nodes voted differently, they would send one vote to one node and one vote to another, but like each node only sees n votes. It's not like it's not like the total number of votes would be 4n over 3.
Does that answer your question?
Yes, I think so, but how do you know that? How do you know that the same node is not sending 2 votes to you as just like one receiver of votes without a signature?
You could, like, so okay, so let's go back to the protocol, right? So what happens if
I didn't understand the question.
I guess so. Let me try to. I also didn't fully understand the question, but let me try to clarify what I think is the confusion. So during the protocol, if I receive, let's say Junxi is one of the corrupt players, and she voted for both 0 and 1 to me, I'm just going to I'm just going to basically say these are 2 votes, right? Junxi voted for both 0 and 1. And when I tally the votes, I will tally both. I will say, okay, how many people have voted for 0? I will count Junxi's vote. And when I tally how many people have voted for 1, I will count Junxi's vote again, because Junxi voted for both bits. So that's okay. I mean, in fact, it doesn't matter what you do. Like, you can also say, okay, Junxi voted for 2 different bits. I'm only going to take the first one. Like, if Junxi voted for both, I'm going to treat that as 0. So that's, like, no matter how you interpret it, the protocol is still correct. Like, I can also interpret it as Junxi voted for both. I know she has to be corrupt. I'm just going to drop her vote altogether. And that works too. So in that case, like, it doesn't matter how you behave. Like, you can completely ignore all messages from Junxi if you are convinced that she's corrupt. You can take both of her votes in the tally. You can pick an arbitrary one as well, right? And no matter how you treat Junxi's 2 votes, this lemma would still hold. Lemma 1 still holds.
I guess my question was, how do you prevent Sybil attack kind of situations if you don't have signatures? That is, one player sending 2 messages to the same. I mean, you have to be able to say that I have received a message from sender 0, and sender 0 will not again send a message to me if the message is not signed.
If Junxi voted for 0 10 times, that's only going to be treated once. Like, the same player cannot cast 10 votes, right? The channel is authenticated. So if Junxi sends a vote to me, I know for sure it comes from Junxi. If she sends 10 votes to me, that's the same as sending 1.
Okay, so the channel is doing the deduplication for a...
Yes.
Okay.
Okay, so that's a great question. Any other questions at this point? I guess like now is actually a good time to maybe think about the protocol. You know, if you have any questions, please ask.
Can you send out the Scribble link to the chat?
Oh, yeah, sure. Sorry, I forgot to do that.
Sorry, I have a question.
Yes, please go ahead. Let me also send the Scribble link.
So if we know for a fact that the number of correct players is strictly less than n/3, is there any strict advantage that Dola Strong offers over this protocol, or is this protocol just like strictly better?
This protocol actually, in terms of round complexity, this one is better.
Yeah. But like, are there any other parameters on which we kind of like compare protocols on which Dola Strong might be better if we actually do know for a fact the number of correct players is less than n/3?
I mean, this protocol, like from a theoretical perspective, this protocol is randomized. Like, you know, I mean, even let's say in the ideal signature model, right? So like, Dola Strong doesn't have randomness coming from the signature. So Dola Strong gives a deterministic guarantee, but this one gives a randomized guarantee, which you'll see at the end.
Okay, thank you.
But you can like, what we didn't talk about is like how to set the round K, right? Like we said, the protocol is going to be run for K rounds. And essentially every round, like, you know, we are amplifying the consistency. So the more rounds you run the protocol for, like, you know, the higher chance you're going to get consistency and validity. And then the failure probability we will show drops exponentially fast with respect to K. So if you run it for, let's say, 80 rounds, like, you know, with like something like 2 to the 80, 1 over 2 to the 80 probability, except with 1 over 2 to the 80 probability, you will get the security properties. I mean, the constant is not 2. We will show it's not 2, but, you know, you can think of it as like, except with 1 over 2 to the 80 probability.
So it'll be like a boosting argument, right?
Yeah, so this will be like the rest of the proof, essentially. Once we go over the proof, you'll see like where this comes from.
Okay, thank you.
Okay, so any other questions about the protocol? Like, I guess clarifications about the, you know, the channel was very important for sure. Okay. Okay, so this essentially says, you know, at the end of every iteration, people cannot have completely opposite beliefs. So how do we prove consistency and validity from this? So let's prove our second lemma. And what is the second lemma? So if we think about the protocol, let's define something called a lucky iteration. So we say an iteration is lucky if, let's say, the leader of the iteration is honest, iteration R is lucky if LR is honest, and moreover, LR proposes the bit B in iteration R. And at this moment, at the beginning of this iteration, no honest player has the belief 1 minus B. So, okay, so no honest player has the sticky bit Okay, so why do we want these nice conditions? If leader is honest, he will propose the same bit to everyone, right? He's not going to propose different bits to different people. And the second condition is nice because like this kind of says the leader's proposal is weakly consistent with everyone's belief, right? It's, you know, either the leader proposed B and my belief is bottom, I don't have a belief, or the leader proposed B and my belief is exactly B. And in either case, I'm just going to like, you know, vote in a way that's consistent with the leader's proposal, right? So either, you know, if my belief is consistent with the leader's proposal, I will vote on my sticky bit, which is consistent with the leader's proposal. If my belief is bottom, I don't have a belief, in this case, I'm just going to listen to the leader and I will vote consistently with the leader's proposal as well. So now I'm going to ask you to think, you know, if let's say these nice events happen, what's going to happen for the rest of the protocol? Like suppose at some point, this very nice event happens, we have an honest leader, the leader makes a proposal that's in some sense weakly consistent with everyone's belief.
All honest players will have B as their sticky bit in next round.
Yes, and then one more step. So they'll have the sticky bit B in the next round, and then what's going to happen in the next round? What do they vote on? Like, what do all these honest
They
people?
will all vote on B
Right.
in the next round because their sticky bit is B. So if
Yes.
you end after 2 rounds, then we have the one of the property. I forget it's either validity or the other one, but like they will all vote on the same thing.
Yeah. So essentially, like, you know, as you can see, so let me repeat what Junxi said, right? So if these nice events happen, what happens is in round R, you know, what are people going to vote? All the honest nodes will vote for exactly B. So therefore, everyone will have heard 2/3 votes on B, you know, in the last round of the iteration. And therefore, everyone will modify their belief to B by the end of iteration R. So now, if all the honest players' belief is B, what are they going to vote on in the next iteration? They're all going to vote on B in the next iteration too, like regardless of what the leader proposes in the next iteration. So at the end of the next iteration, every honest node will, you know, set their belief to B again. And this just goes on essentially till the end of the protocol. So if this nice event, this lucky iteration ever happens, it says, you know, at the end of the protocol, every honest player's output will be B. Okay, so I can write all of this down. Okay, so now we have the second lemma, right? Previously it was lemma 1. So let me call this lemma 2. Suppose that iteration R less than K is lucky. And in this lucky iteration, the leader proposes the bit B. Then we can conclude every honest player sticky bit at the very end of the protocol must be B. So in other words, if a lucky iteration ever happens, then we are all good in terms of consistency. We haven't proved validity yet, but at least as far as consistency is concerned, like all we need is just one lucky iteration, and we can guarantee consistency at the end of the protocol. So the proof of this is like just as Junxi said, because if a lucky iteration ever happens, you know, you can check the protocol rule, right? So essentially in iteration R, what does everyone vote on? Every honest player votes on B. Because either my sticky bit is B, I vote, you know, according to my sticky bit, or if my sticky bit is like, it cannot be, my sticky bit cannot be 1 minus B, and that's like, by the definition of the lucky by the definition of the lucky iteration, right? My sticky bit cannot be 1 minus B, right? It's either bottom or B. So if it's bottom, I listen to the leader. If it's B, I vote on B, right? So I'm just going to vote on B regardless. So that's at the end of iteration R. Everyone modifies their sticky bit. So every honest player, I should say every honest player sets its sticky bit to B. And why is that? Because if honest players, they all vote for B, I'm guaranteed to collect 2/3 votes on B, right? If I collect 2/3 votes on B, I will modify my sticky bit to B. Okay, so now essentially the same happens the same will happen in iteration R minus 1, 2. So R plus 1 in iteration R plus 1, 2, right? And why is that the case? Because at this moment, all the honest players' sticky bits are set to B, and in the next iteration, they just vote. They're going to vote according to their sticky bit, no matter what the next leader says, right? Even if the next leader is malicious, it doesn't matter. Even if the next leader proposes, you know, a different bit, it doesn't matter. I'm just going to act according to my belief. I will vote for B, and then at the end of the next iteration, because all the honest players voted for B, I will have collected 2/3 votes on B. I will set my sticky bit to B again, and so on. And you know, again, no one, if someone receives 2/3 votes on B, no one's going to receive 2/3 votes on 1 minus B, right? So everyone sets their sticky bit to B. Okay, so now what, right? So we've shown if this lucky iteration ever happens, we get consistency at the end. So all it remains to show is that this lucky iteration will actually happen with very high probability. So how do we show that, right? I'll let you think about it yourself. Like, you know, this is related to the parameter K. So I want to say if the number of iterations K is large enough, then with very high probability, there has to be a lucky iteration. And just to help you, let's go back to the definition of lucky iteration. What does it take to have a lucky iteration? You know, the first requirement is that the leader is honest, right? So if every iteration we are picking a random leader, then, you know, with 2/3 probability, this leader is going to be honest. But I mean, we do need the second requirement, which is that the leader proposes a bit B that's weakly consistent with everyone else's belief. So now to satisfy the second condition, like essentially there are two cases, right? So if case one, you know, if this honest leader, let's just assume somehow the leader is already, you know, by chance we are happy we have an honest leader. And now there are two cases. Case one is when the honest leader has a sticky bit, which is not bottom. In that case, the leader will propose its sticky bit, and we know that this notion of weak consistency is guaranteed, because if the leader actually has a sticky bit B that's not bottom, by lemma 1, we know everyone's sticky bit cannot be 1 minus B, which we proved earlier. But case 2 is if the leader doesn't have a sticky bit, like the sticky bit is bottom, essentially, then what happens? Then the honest leader will propose a random bit. And what's the chance that this random bit is going to be weakly consistent with everyone's belief? I mean, as we said, by lemma 1, everyone's belief cannot be completely opposite, right? So there's like, it's possible everyone believes in bottom. It's possible that some believe in 1, others believe in bottom. In that case, with probability 1/2, I'm going to pick, 1, right? Which is what people's beliefs are. And the same with, it's possible that some people believe in 0, others believe in bottom. And in this case, I will happen to pick 0 with 1/2 probability too. Okay. So it seems like, essentially with every iteration, there's some constant probability that this iteration is going to be lucky. So that's our third lemma. The third lemma is basically just saying every time there's a new iteration with some constant probability, this iteration is going to be lucky. Lemma 3. Suppose the hash function h is chosen independently of the corrupt nodes. So imagine like the adversary chose the corrupt players first, and then we choose this random oracle. Then for every iteration, so regardless of what the previous, whether the previous iterations are lucky, hold on. We know that the rth iteration is lucky with probability at least 1/3. Okay, so suppose, before I prove this, suppose this is true, then essentially if we run the protocol for k iterations, what's the chance that all k of them are unlucky?
2/3 to the power of n.
Yes, so if this is true, note that if this is true, then the probability that all k iterations are unlucky is at most 2/3 to the k, right? So as you can see, this expression is exponentially small in k. So if I set like k to be 80 or 128 or maybe 256, then the failure probability becomes extremely tiny. So I don't have to set K to be too large, and then I'm guaranteed that with, you know, overwhelming probability, there has to be a lucky iteration. And once we have a lucky iteration, as we proved in lemma 2, we can guarantee consistency at the end of the protocol. Okay. So essentially, you know, to prove consistency, we haven't proved validity yet. To prove consistency, we only have to prove lemma 3, right? So how do we prove lemma 3? I kind of already told you the proof, but now let's write it down. Okay, so note that all of the following hold. Regardless of whether, like, essentially even when conditioned on whether previous iterations are lucky or not.
What do you mean by condition on whether previous iterations are lucky or not?
I mean, like, essentially there's fresh randomness that's like, I don't want them to, you know, it could be that every epoch is lucky with probability 1/3, but, you know, they're dependent. So like all of them are either all lucky or unlucky, right? So it's not like I mean, what I want is every time I flip a fresh random coin to decide whether it's lucky or not. So this just
For the
gives
previous
you
round?
Yeah, so I want to make sure it's kind of like every iteration I flip a coin, and with 1/3 probability or more, it's lucky. So it's there's independence in the new coin flip.
So like when you flip a coin, the 1/3 probability is for current round to be lucky or for previous rounds to be lucky?
The current. I want every iteration to have a fresh coin that decides whether it's lucky. Because it could be like, okay, I flip a coin, a single coin, and if it's heads, then every epoch is lucky, and if it's tails, then every epoch is unlucky, right? So in this case, every epoch is still lucky with probability 1/3, but it doesn't allow me to make like the argument you have said, like this calculation. This calculation relies on independence. Like it's like I want a random process, which is like every iteration I flip a random coin that decides whether this iteration is lucky or not. And with 1/3 probability, you know, it's at least 1/3 probability it's going to be lucky.
Got it.
Okay. Okay, so that's a great question too. Okay, so now observe the following. In every iteration R, so if, let's say, the leader happens to be lucky, if the leader happens to be honest, and its sticky bit is not bottom at the beginning of the epoch, at the beginning of the iteration, so if this happens, I claim this epoch must be lucky. This iteration must be lucky. Then iteration R is guaranteed to be lucky. And this is guaranteed by lemma 1. And remember, lemma 1 says that people cannot have completely opposite beliefs, right? So in this case, if the leader has a non-bottom sticky bit, then every honest player's sticky bit can either agree, be the same bit, or it can be bottom. And regardless of which case, right, the leader is going to propose the 6 sticky bits, and no one can have a completely opposite belief. And therefore, in this case, this iteration is lucky. Okay, so now, in the second case, the leader happens to be honest, but its sticky bit is bottom, right? So if we conditioned on the second event, if leader R is honest and its sticky bit is bottom at the beginning of the iteration, in this case, we can conclude, I claim with probability at least a half, this epoch is going to be lucky, right? I claim that with probability at least a half, right, conditioned on this being true, then with probability at least a half, and this probability is coming from the LR's coin flip, right? So over the choice of the leader's coin flip, this iteration will be lucky. And why is this the case? And note that this here again, we need to use lemma 1. Okay, so why is this the case, right? If the leader is honest, but it has a bottom sticky bit, in this case, it's going to decide the proposal at random, right? It's going to flip a random bit and propose that bit. And, for all the remaining honest players, they can have at most one belief, right? Their belief can be bottom, that doesn't matter. But if they have a non-bottom belief, there's only one consistent belief according to lemma 1. So I just have to be lucky and pick that belief. If there exists a belief among, other honest players, I just have to be lucky to pick that bit. And in that case, this iteration will be lucky too. Okay, so finally, so all of the above is assuming the leader is honest, right? So we are kind of lucky we picked an honest leader. But to conclude this lemma, we need to observe that with probability two-thirds over the choice of the random oracle, every epoch, every iteration R has an honest leader, yeah. And this is because there are two-thirds honest players, right? Fewer than one-third are corrupt. So there's like, if you pick one person at random, with probability two-thirds, this person is going to be honest. Okay. So now the lemma follows. Essentially, in other words, every iteration is lucky with probability at least two-thirds. Two-thirds is like the probability that the leader is honest. and condition on the leader is honest, there is at least a half probability over the choice of the leader's random coin that the iteration will be lucky, right? So this gives me 1/3. If the leader is lucky, right, remember there are two cases. Like case one, we don't have to worry about because case one is guaranteed to be lucky, and case two, there's a half probability that it'll be lucky. Okay, and then the leader is honest with probability 2/3. So that's why we get this calculation. Okay. So that's actually the consistency proof, right? Because we have shown with extremely high probability, there's going to be a lucky iteration. And then earlier we showed that as long as there's a lucky iteration, at the end of the protocol, all the honest players are going to output a consistent decision. So just to revisit our question, right? So like there was a great question that, you know, how does this protocol compare with Dou left strong? One point is that this protocol gives a randomized guarantee, right? So basically the probability of security failure is exponentially small in the number of rounds. But whereas Dou left strong, you know, it gives a deterministic guarantee, assuming like the signature is ideal. But otherwise, you know, in practice, we are often happy with like a probabilistic guarantee because, you know, all of the crypto, most of the crypto is probabilistic anyway. So all we have to do is just to set K to be large enough and to have the failure probability be really, really, really tiny. Like the failure shouldn't happen, you know, once every 1,000 years. And that's also like the fundamental idea behind crypto is the same. Like all these encryption schemes, like there's a tiny chance you can happen to brute force the secret key, but that shouldn't happen, you know, once every 1,000 years. So this, you can do the same. Okay, so I've proven consistency. I haven't proven validity yet. But I'm not going to do that. I will ask you to prove validity yourself. So remember, you know, there's some parts of the protocol we haven't used, right, in the consistency proof. Like as we said, this is also like often the part that, like, I always forget about the first round, right? We said the first iteration, the honest the first iteration, the designated sender is going to be the leader. And then initially,
does it mean like initially, if the designated sender is honest, then this is a lucky iteration already?
Yeah, exactly, right? So the validity proof is one line. I mean, given what we have already proven, so you essentially set it out. Right?
You didn't put it in the homework, did you?
No, it's in the book, but it's one line, just like you said, and that line is exactly as you said. If the sender is honest, then the first iteration will be lucky because the sender's sticky bit is initialized to its input bit, and initially everyone's sticky bit is bottom, right? So the first epoch will be lucky if the sender is honest, and then because the sender is proposing its input bit, it guarantees that at the end of the protocol, everyone will output the sender's input bit, like by, I think was it lemma 2 or lemma 3 that we proved? By lemma 2, yeah. By lemma 2, then at the end of the protocol, everyone will output the sender's input bit. Any questions at this point? I guess this is what I want to cover in this lecture. So that's the kind of the end of the lecture. But if you have questions, I'm happy to stay longer and chat more. this is in fact a very simple like consensus protocol. Like in your consensus simulator, this can also be another candidate if you want to like implement examples. And this protocol works in the synchronous model. You know, the model is the same as Dolaf strong, right? If honest player sends a message, the honest recipient will receive it at the beginning of the next round.
Hi, I have another question, sorry.
Yes, go ahead.
So for this protocol, we kind of assume that we have these communication channels that are secure and we can kind of verify who the votes are coming from in some sense. And so I was wondering, is there a protocol which achieves like similar performance without that particular assumption?
You mean if the channel is unauthenticated?
Yeah.
So if the channel is unauthenticated and there's no other setup assumption, it's actually impossible to reach consensus. I have a proof, like in one of my papers. I can send it to you offline. Can I ask who's asking this question?
It's Anubhav.
Anubhav. Oh, okay, thanks. Yeah, so I can tell you the intuition is actually simple. It's exactly the Sybil attack question that was asked earlier. So if the channel is unauthenticated, then I can impersonate, you know, Junxi, I can impersonate Lisa, Ke, I can cast many votes.
Oh, I see. Okay.
But that's not a formal proof. Like if you want to formally prove that it doesn't work, it takes a little bit more work.
Yeah, okay, no, but I think the intuition is useful. Thank you.
Yeah.
Also another thing is in the very beginning, when you mentioned first theorem without PKI or setup assumptions, what do you mean by setup assumptions?
So like PKI can be regarded as a setup assumption, like it's because you have to have an infrastructure that distribute people's public keys, right? So like in the Dolaf strong protocol, we assume that everyone's public keys are common knowledge a priori. Like before the protocol starts, everyone knows everyone else's public key, and somehow this key distribution is like actually done in a secure channel that just magically happened. Like we never worried about how to distribute these keys. So that's a setup assumption. So like in general, we call like any type of assumptions like this, like if you have to distribute keys a priori, we call that a setup assumption. Like I just want to be a little bit more precise because, you know, I said without PKI, right? But you could like, you know, throw in something else, like that's a variation of PKI or something. So, but I'm saying like without any of these.
Okay, got it.
Yeah. Okay, so if nothing else, I'll see you next Tuesday. Have a nice weekend.